So as we look here, and again, Ellie, this is just kind of review for everything here. If there's any question that you have here, Ellie, stop me. As we look, at these, this is kind of a lot the same way that we were looking at the composite construction here of the velocity that we're building, which is kind of cool. The one thing is just kind of brush up on the components of the wing. That will be some stuff commercially that you'll kind of be held responsible for that we haven't necessarily, been in the past. All of these are all, my Lord in heaven, they should all be pretty just old hat to you. Conventional gear is what we call tail wheel, otherwise it's tricycle gear. The mains, nose gear, retractable gear, the gear that you have on your Mustang. It's a trailing link suspension, phenomenal gearing system. It's very, very cool. Even when you plant that bad boy on the runway, it still makes the pilot feel like a hero, which is pretty awesome. That's what it's all about, really. I mean, if you think about it. One of the things that I'm going to have looked at on my airplane is this shimmy dampener right here, because I'm getting a vibration as I'm headed down the runway for some reason in my nose wheel. So I'm going to have to get that checked out. The brakes, remember, basically the brakes on your airplane are about pound for pound the size of the brakes on your bicycle. Keep that in mind. Everything that we do in the air, on the ground, energy management, that's the key. We will actually use the formulae to really discuss that energy management component as we start the commercial side of things. And so the big thing there is that we want to make sure that we're managing our movement here with throttle every chance we get, and only relying on the brakes when we have to. Whenever you have to apply a brake, it is basically to admit defeat. And so that's kind of what we do. Engine, propeller, we look at those things. There's a cirri. This is when you look at that and you kind of scoff and you go, peasants. And that was a big thing with your dad. I asked him about that. And I said, Tom, dude, you were family with Cirrus. You've got to be persona non grata now that you're burning kerosene. And he had a concern about that.
I know, we were very concerned because last year we were looking for a plane, so we were invited to everybody's barbecue. Everyone.
Yeah.
It was great. Now we're just not.
Well, now you guys are just going to have to slum, and you're just going to have to come to our barbecue. That's just what you're going to have to do. Doggone it. Yeah, you may be eschewed by the Cirri crowd, but I have a feeling that you'll get over it. Yeah. So engine, understand the different types of engines. We really, when we get here, Ellie, to the commercial side of our stuff, we're going to examine engines in more detail, especially when it comes to the power ratings and the power output. Not just what the book says, but how we can also use mathematics to predict what the actual performance of that airplane can be. And you look at these, and so you understand, the radial engines that you have that came out, back in the day. Inline, which are going to be the upright engines. Horizontally opposed, which is what you find in most aircraft. There are some V configurations with the cylinder configurations on there. Most automobiles, their engines are aligned in sort of that V-shaped configuration. The primary reason is because of the fact that you can actually work on those over the fenders without having to actually pull the engine to work on them in a car. Whereas with an airplane, we kind of don't care because we can pop the cowling in 30 seconds and we can get to everything that we need to on the airplane, which is why the horizontally opposed normally is a little bit better solution for us. So in the Diamond DA40, for instance, as in the little stationary here, they are going to be horizontally opposed. The Diamond is going to have 4 of those cylinders. Mine has 6. The basic principles of a reciprocating engine. Reciprocating, if you just think about the definition there, it's like if it does one thing over here, it does another thing over there. That's kind of how it happens. We have the 4 strokes of a 4-stroke engine. Do you remember what they are?
Intake, compression, power.
Exactly. Intake, compression, power, and exhaust, or as they say down at the shed, suck, squeeze, bang, blow. That's kind of the way that they do it there. But we will refer to it here in academia as intake, compression, power, and exhaust. So we have that little piston thingy, what slides kind of from the back end to the top end. And again, that's kind of relative here because it's going sideways in our engines. In the very center of all of this mess is going to be our the crankshaft. The crankshaft is enclosed here in the crankcase. And then we have the connecting rod here that is going to connect the actual funky shaped crankshaft to the actual piston itself. The piston itself is that piece of metal that slides, in this case, left and right, or toward the crankshaft and away from the crankshaft. We have our spark plugs here on the top and the bottom. Now, the reason that we have 2 spark plugs here, Ellie, is for what? The hand gestures are lovely, by the way.
Thank you.
I felt like I was at like a luau.
Yeah.
I saw the, with all of that. That was great. So, those spark plugs are there for what?
To ignite the spark.
Correct.
Yeah.
Yeah, because in order to have combustion, you got to have air, fuel, and spark.
Yes.
So the spark ignites the air and the fuel, and that kind of makes stuff move in that engine. So when we look at this, we have 2 spark plugs because we have 2 magneto systems. The reason that we have 2 magneto systems as opposed to 1 is for what?
2 is 1 fails.
Okay, for a redundancy. Okay, so we have that as kind of a backup. Second is performance. It's performance. Okay, those are the 2 reasons. So that that when we have, and you can look here, when you have the actual combustive event happening simultaneously from here and from here, then what happens is that it moves like this, as opposed to kind of this mushroom thing, which takes time, and it's not as efficient. You don't wind up burning all of the fuel and air in there with just 1 spark plug. But it's enough to kind of keep the engine going. So if one fails, you are going to have reduced performance, and you have to consider that. But with both of them going, you have improved performance because now you have a better shaped combustive event. That fire arc, as it moves through that cylinder moving together, is more efficient. So that's kind of why we have those 2 there. Now, the one negative thing about this is that by having a spark plug at the top and then 1 at the bottom is this. The bottom spark plugs have a tendency to foul quicker than the top ones. Do you remember what fouling is on a spark plug?
Just not working.
So what happens is that, let's say for instance you're running your system too rich, too much fuel for your altitude and your power settings. You can't burn all of that stuff in that combustion chamber. And there are remnants that are left behind that don't go out in the exhaust phase. They sort of stick around. And where they tend to stick around is at the tip of the bottom part of that spark plug. So you want to get that carbon gook around there. So if you're running your engine too rich, especially on the ground, up here, then you have a tendency to kind of foul those plugs. Now, that's not to say that a mechanic has to pull them and clean them and put them back in your airplane and off you go. Sometimes it comes to that. But you can, simply by leaning and then putting a higher power setting there, you can effectively burn that stuff off and get things acting the way that they're supposed to. It's one of the reasons that we do an engine run-up, is to make sure that both of those systems are operating at their peak performance. Because when do most accidents occur? Takeoff and landing. We want to minimize any of those risks that we have here, and making sure that we've got a good spinny thingy happening out there is the big deal. So that's what we want to do. So as we look here, again, spark plugs, intake valve, exhaust valve, and the combustion chamber where the air can come in. Now in this case, there's a couple of different ways that can happen. With this fuel coming in some cases, remember with the carburetor, you're pulling the fuel and air mixture in simultaneously, because that's kind of what the function of the carburetor is. In a fuel injected system, then what you have happen is that you have a valve that is going to be part of that kind of what we call the top end, it may be the side, the outer parts of your cylinder, where there's a nozzle, and that fuel line is connected directly to that nozzle, and it sprays a metered amount based on the timing of your engine, the power settings, etc., for that optimal flow. So you get air coming in the intake while simultaneously fuel is squirted into that combustion chamber. So that's kind of the differences that you have there. So with this, so in the intake valve, this creates a negative pressure inside the combustion chamber, pulling in the fuel and the air, okay? The intake valve is open, okay? Then it reaches the bottom of the cycle and it begins to compress. It moves this direction toward the outside portion of the combustion chamber, and it squeezes that fuel-air mixture together. Why do we squeeze the fuel-air mixture? You can talk louder. It's okay. You can speak up. It's just us.
Okay. Like condense everything, and that way you can
Condense may not be the right word. Compress. We want to compress everything. Why do we want to compress it? Give me a gunpowder example.
like I don't know how to
Let's just say this.
like this.
Okay, let's say I want to blow something up.
Okay.
I'm going to use gunpowder to do it. If I just pour a bunch of gunpowder over here by this thing I want to blow up, and I just dump it in a pile, and then I light it, what's going to happen? Just like that. Okay? There is nothing to direct the energy that I have just unleashed. Nothing. But now let's say that I want to make a noisemaker. I don't know, kind of like a firecracker. Okay? Now what am I going to do with that gunpowder?
Now you need to direct the energy.
Okay, all right.
Blow it up.
Okay, so I'm going to take that little bit of gunpowder and I'm going to wrap it really, really tight in paper. Okay, then I'm going to put a fuse in it. Light that fuse gets down here and it ignites this gunpowder while it's under pressure. Now what happens?
Now it's
Bang! Okay, there we go. That's kind of what happens. Now you've got something. Because now you have something where you can now begin to direct that energy as opposed to just release it out, into the universe, right? By compressing the fuel and the air, we create an opportunity for a far more efficient combustion to occur in that chamber. Not only that, but we're actually coiling the spring, almost, if you think of it that way, so that then, with that combustion piece, now that is the driver of everything that makes everything in your engine work. So that we want the most efficient form, and we don't want to call it an explosion. I'm just still going to call it combustion. So that it sends that energy back toward the crankcase. And that's what spins it. The reciprocating piece is that, again, while all of that's happening in one cylinder, we have all of these other things happening in these other cylinders simultaneously, so that we get, all of that real rapid movement of those cylinders timed to make the spinny thingy go. Okay, so that's kind of why we do it. So that power stroke, that's the part where, again, spark plugs have sparked, controlled combustion, shoves that piston back toward the crankcase. Then in the exhaust phase, now we're exhausting stuff. The whole process, I think we can both agree, is exhausting. But what exactly are we exhausting?
The remnants of the fuel-air mixture.
Okay.
And the exhaust valve opens and they go out.
Okay. What else is going out besides any byproduct of combustion? What else is going out? I'm thinking today is a rough day because this morning in that first class today, I had three girls over here. Two of them couldn't keep their chin off their chest.
It was a rough day. I thought it was Friday.
Yeah, yeah. So I kind of get that. Heat. Heat. Because when something blows up, it's going to get hot, right?
Yes.
There we go. So that heat escapes that combustion chamber. Now, do we care? This time of year we care. Why? How are you going to keep that airplane warm inside that airplane when you're flying?
That's true. You can use that heat.
So what we do is this. Through that exhaust pipe, surrounding the pipe itself is this hollow chamber called a manifold. That manifold, then, the heat that is coming through that exhaust pipe, is then that air within the manifold is heated. We can then, with a little fan, pull that heat in that hollow manifold into the cabin to keep us warm. Ah! But it's not without risk.
No, carbon monoxide.
How could carbon monoxide enter the equation here?
If it is not, the heat isn't held properly, then the byproducts of the fuel-air mixture, chemicals come through, which can make issues happen. Carbon monoxide.
It's all about the issues.
Yes.
Let's say, for example, you have an exhaust pipe that gets heated over and over and over and over. Over time, you're going to have metal fatigue. When you have metal fatigue, what can happen?
It's not possible.
You can get a little bitty hole in that metal. Well, if you get a little bitty hole in that exhaust pipe and you have some of those gases escaping out here that could ultimately be captured in that manifold, you could then suck those chemicals into the cockpit. And I think we can both agree that would be bad for your health, right? Carbon monoxide poisoning, as we talked about in the physiology section of everything that we've done here thus far, right? So we have to be careful. We have CO detectors in the airplane. Some of them are electronic, some of them can be a simple little card to kind of let you know. But there are some telltale signs that we're starting to get sick. Okay, you got to remember what those are because those are also going to be on the test. Okay, just the physiology piece. So we try to use some of that heat, some of that escaping energy there to kind of help us on this other side. There's another thing that we can bolt onto that engine that can improve the performance even more for our engine that also takes advantage of that escaping hot gas, that hot air coming out of there. It's called a turbocharger. So we put these two turbochargers on the sides then of these engines. That escaping gas can turn a turbine, and it can basically pull additional air for use inside your engine. Because in this engine that we're looking at here, the only air that's available is just the ambient air pressure that there may be outside. You know, whatever we can kind of pull in, that's going to be it. We don't have any way to really force more air in because we can actually create better performance if we can get more oxygen molecules, meaning we got to get more air volume in that thing. But in this case, we can only take just sort of what the engine itself can kind of pull in. But if we take a device and we bolt that onto the side of that engine, that can use some of those exhaust gases to turn this impeller, to turn this thing that can reach out there and suck in more air, well, guess what? I can create sea level performance now up to a certain altitude, let's say 17 or 18,000 feet. So now I can get my engine working more efficiently with higher performance to a higher altitude. So that's another way that we can use those exhaust gases. Now, so there's our review, the 4 strokes of a 4-stroke engine. Be prepared to draw this if necessary. Sometimes designated pilot examiners, when they're doing that oral phase, and they like to really see and I have heard this more, Ellie, from girls. Sometimes these dinosaur DPEs, everybody brings baggage to the discussion. Sometimes they think, okay, a girl is not going to understand these systems the way a boy can. Them's fighting words, girl. Okay? So be prepared to explain that. I know you will. Valves and valve timing. We talk about the valve timings when they open and close. And if you think about the cycles, and what's interesting is that we look at it sort of linearly, you know, like here's the beginning, here's the end, but remember it's a loop. So we see the exhaust, the intake valve open on the intake side, and then it's closed until it opens again. And then, so on number 1, we have an exhaust valve open. Excuse me. Number 1, we have the intake valve open. Number 4, we have the exhaust valve open, right? But then what's next? Number 1. So then on number 1, so then you have the exhaust valve, so it's like titting, 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 and you have to have that timed so that they open and close when they're supposed to. So you have a camshaft that basically turns that, not the crankshaft, but the camshaft that ultimately then helps turn, open and close those valves that are spring-loaded to make those things go when they're supposed to. And when you look at this, if you think about how many times those things open and close, if you've got an engine that rotates, like for instance my airplane in cruise, it'll cruise at an RPM of 2,400 RPM, meaning that, you know, it'll go 2,400 circles in a minute. That means that those valves open 1,200 times in 60 seconds. That's 20 times a second. So these babies are moving. So you can see why the timing of everything is so important. This kind of shows that timing piece on a typical valve timing cycle in a 4-stroke engine. The ignition, how do we turn the thing on? Well, there we go. In this case, we also have it not just to start the engine, but we have the dual ignition with the dual mags, as we just described earlier. You can look at those as you will. The starter, this is that thing that goes to the main battery. Remember, the main battery in the system exists to start that airplane. That is its primary function. The main battery on the airplane exists just to start that engine. Beyond that, it is kind of an electrical pass-through to stay charged so that in the event of an electrical failure, you can use that main battery to supply electricity to your instruments for a certain period of time. But its primary mission is for starting the airplane, and then secondarily, the main battery is there to supply electricity to your instruments in the event of a failure of the alternator, by the way. Okay, you can read that. Impulse coupling. We don't really get into the impulse coupling here as well, but I think it's just understand that kind of what it is. And basically kind of what it does is that it sort of provides that little extra juice almost to kind of help start the engine here also. So it's almost like a little electrical boost pump thing almost. Kind of, that's sort of the way that it kind of works. The ignition switch you're familiar with. Primarily you have right, left. Those are going to be the mags. Both. This is where you are in cruise. And then start, this is where you go to actually start the engine. Once it's started, you let the key go, and the spring will pull it back here to the both position. We check both right and left during our engine run-up. Always treat a propeller like it's live. We talk about the grounding. Did we talk about the grounding? I think you asked the question about the grounding and the ground wire. Okay, we've got that. Exhaust system, we talked about oil. Primary reason that we have oil in the engine is for what?
Oil lubricates, clears, and cleans and seals.
Okay, lubrication, that's number one. Cooling is going to be it. Also, it removes debris, runs it through the filter, things like that. Keeps everything kind of lubricated there as well, kind of helps keep the seals working properly. So that's kind of what it is. This is an illustration of what a typical oil system might look like. Oh, also the reduction of friction. That's the other thing there. It kind of keeps stuff moving. Talk about that. Oil properties, maintenance. It's interesting because we talk about oil. There are oils out there now that are what they refer to as like a 15,000 mile oil. The weak link in the system right now is the actual filter. That filter media that is in there that captures all of those particles with things is still the most effective media in those filters is kind of a paper media, you know, that allows that oil to kind of get squished through there and squeezed out and then brought back into the system. And then that paper media captures all of those particulates and things so that it doesn't reintroduce them into the system. During an oil change, that filter is removed and we cut them open and we unroll all that media. And the mechanics, they look at this and they'll look at any traces of metals and just kind of see what there is. We also send the oil in for analysis occasionally. We don't necessarily do it on every oil change, but we do that to send it in for analysis, especially when you're breaking in an engine and you want to make sure that everything is working properly and your engine is not what we call making metal. So we want to make sure that that's not occurring. But if it is making metal, we look at it in this strip. Some of the parts inside the engine, like the piston, the cylinder, and the rings specifically, can be made of different metals that are different color. So if we start noticing different colors of things in here, you can actually look at that and say visually, to say this is what something is rubbing in here. Something is not seated properly. For whatever reason, something is scraping, and we can kind of tell what it is so that your mechanics can then diagnose the problem and then ultimately try to fix it. So that's one of the things with regard to the filters. The manufacturer, the engine manufacturer, recommends the type of oil that we used to use. It used to be that in the summertime we would run a really thick oil in the summer because the temperatures were so much warmer, and we'd run a thinner or lighter oil in the wintertime because the temperatures are colder. Now basically the oils are such that we have a type of an oil that we just run year round. It's an all temperature kind of an oil, and it's great. You know, you don't have to worry about it. The more things you try to switch back and forth here with an oil, the engine kind of gets confused. It also gets a place where it kind of likes a certain amount of oil. For instance, in the diamonds, it'll hold 8 quarts of oil. We never have the mechanics of an oil change put 8 quarts of oil in it. And the reason being, it doesn't like that much oil in it. There's so much pressure through there that in that first hour of operation, it'll puke out through that oil, the oil drain piece, which is kind of an overflow type of a thing. When there's too much pressure, it pushes it out. It'll puke out a quart of that oil in the first hour. It'll get down to like 6.5, and that's where it's happy. My airplane will hold 12 quarts of oil. 10.5 is where it's happy. I've run that airplane now for 20 hours that I've had it. It's at 10.5, and that's where it stayed. nice honey brown, looking good, you know, so everything, so it's just kind of where they like to stay. But you do have certain engine requirements to say you can get this down in the diamond to 4 quarts if you're on VFR, but you've got to have a minimum of 6 quarts if you're flying IFR. So you may have manufacturer restrictions on the oil level that you have based on the type of flying that you're going to do. So you've got to know that as well. The oil system, we looked at this. Wet sump, dry sump, you can read this. Little wet sump, dry sump. It's always a little something, something, right? That really wasn't that funny. So, filters, all of these things, you can look at this. You've been through this, you've read it. Understanding, of course, that every time that you fly this airplane, you're checking the oil before you fly it. And let's just say that you're flying a multi-leg flight. You shut down the engine. You never restart an engine without checking the oil.
Yep.
Never. You always have to check that oil, and you check your fuel before you ever start an engine. Incorrect types, incorrect quantities, you can look at this here as well. Low oil pressure. The biggest thing with low oil pressure is going to be the fact that you don't get the lubrication qualities that you have, and you're going to have some temperature issues with that as well. Gradual oil loss. One of the things that you can see is that, like for instance, what we just talked about is that you have that oil that will stay at a certain level. Well, the one thing that I can tell with that is that, I've got wood right here, is that I don't have a leak anywhere. But if we have some unexplained use of oil where the consumption seems to be a lot, some cases the color of the oil can kind of tell why. If it's like gets really, really black, really quick, something's going on in there where something is getting really, really hot, or there's some kind of friction that's not being addressed in that system. But if the color is good and it stays looking good like this, but now you're losing, you've noticed that your oil level is going down, you may have a leak somewhere. And you may notice that on the cowling or underneath the belly of the aircraft as well. So those are some of the things that we look at just to kind of make sure that we're doing what we need to do. Cooling system. The big thing on these engines is the fact that these are air-cooled engines. We don't have a radiator. We don't have a system that flows through this engine that puts water around there to kind of wick away the heat. It absorbs that heat, goes back to a radiator where it's cooled and then brought back into the system. Ours are just all air-cooled. So assist in that air cooling is that we have holes in the cowling for that air to flow through so they can flow in the front and then kind of out the bottom is sort of the way that they normally work, so that air flows over that engine and then down out the bottom. And it flows through these little cooling fins on these cylinders. And those cooling fins are designed to wick away that heat from that cylinder, pick up that airflow, and to more easily move that air. So that's part of the cooling system that we have there. The engine oil is a cooling system. The engine oil can actually be used to heat certain elements of the aircraft with the cabin. And tell me when we get to a place where we need to stop. Because, for instance, in the Velocity, the engine's in the back. So it's kind of hard to capture that exhaust air to pump that back into the cabin for heat. So at the nose of the airplane is an oil cooler. Well, that oil cooler is going to be that thing that captures that heat. There's that manifold that's over that oil cooler that then is pulled out, and that's where we get the warm air to flow into the cabin for the Velocity. Cool part about that is that we don't really have to worry about carbon monoxide stuff, because that's not what you're going to find as that oil goes through that system. So that's another way that we kind of cool the engine, is with that engine oil. Another thing is that on the actual cowling itself are these things called cowl flaps. They're going to be ways, these little doors that we can open and close to regulate the flow of air through that engine. We like a warm engine. We like a warm engine. We don't like a cold engine. We don't like a super hot engine. We like to kind of regulate those temperatures. We try to find that engine's happy place with regards to these temperatures. Turbo inlet temperatures, exhaust gas temperatures, cylinder head temperatures. Those are things that we monitor to make sure that they're within the manufacturer's parameters of heat. And one of the ways that we can do that is not just kind of from an induced standpoint, you know, where we raise and lower the nose, you know, to get more airflow, et cetera, reduce the power, blah, blah, blah. We can open and close those cowl flap doors to kind of help us with this. Normally in cruise, we want those closed because it's more aerodynamic, and we sort of, by then, kind of have other ways that we can adjust the temperatures in there, primarily with our mixture. So that's kind of how we control the temperatures there, get them nice and happy, and then they remain closed until takeoff again or the go around. So that's kind of how we work those. Another thing that can happen to engines is that training engines are a little less susceptible to this, but turbocharged engines are very susceptible to something called shock cooling. These engines don't like, all of a sudden here you are at full power, you're at cruise, etc. You got nice smooth air, you lower the nose, you go fast because you know what, you can with this. Then all of a sudden you got to slow down to land, and then you yank the power back. Well, you don't want to do that. You want to gradually lower the temperatures of these engines and lower the power of these engines incrementally. Normally, we would look to reduce 1 inch of manifold pressure every minute. So no more than 1 inch of manifold pressure. So what does this mean? Here you are in cruise, you're looking about making your approach and you're landing. Well, you've got to start thinking not just in terms about the altitude that you need to lose, but you also need to think about managing the energy of your aircraft while at the same time taking care of the temperatures of your engine. So you have to plan ahead. You've got to start working that power out long before you would in the Diamond. How are we doing? You doing okay? I feel like I've done most of the talking here today.
It makes sense. I like it.
So, there we go. More coming up here. Cooling, cowl flaps. Why am I doing this? I need to do it this way to make it quicker. Carburetor. We've discussed the carburetor. How do you feel about carburetors?
I think they're important. I like carburetors.
Okay. And again, you'll like my, you remember my toilet analogy there with the carburetor? There you go.
I like that.
All right, there you are. So there's your carburetor. Idling systems, fuel air mixture controls for climb and descents. We know what to do there. We know why we lean with altitude, right? Okay. It's interesting, in a turbocharged engine, we don't necessarily have to, because we can keep that mixture set to full because of the fact that we have that turbocharger pulling in all that air. And by pulling in all that air, we get more oxygen. More oxygen means the potential for more FAR. And so if we get more fuel in there, now we can make more actual power up to higher altitudes. So, but we do lean it. We do start to lean even in our climb out and our cruise climb, and then we definitely lean it once we're at cruise. So we do pull that back, even though technically you might not have to. We understand the mixture, idle cutoff, how to shut off the engine, abnormal combustion, detonation, and pre-ignition. Take a look at these again. Just remember that that detonation detonation is normally systemic, normally caused by using the lower grade of fuel, which is not a problem for us anymore because the only fuel available is 100 low lead. Pre-ignition, however, can be the worst one because that can happen on one particular cylinder, and that can just basically kind of blow off the side of your engine, which that could be spectacular. Okay, so just kind of review those. Carb ice, understand that. Impact ice, that's going to be that thing where if you're in an icing situation where your air inlets may develop icing around the edges for that and cut off the air to your engines, which that could be entertaining. Fuel ice, we normally don't worry too much about fuel ice here, but it can happen. We think in terms of the fuel injector as being kind of a fail-safe for ice, but it can actually happen. You can, it's rare, but you can get that ice, which is why some manufacturers will recommend an additive to fuel to kind of prevent that ice from happening in there. A lot of jet fuels, especially this time of year, will add this product called Prist to the systems. So that may be something that you and your dad discuss there as well. Throttle ice, carb heat, fuel injection systems, we've talked about that. We're so clever. Okay, this is kind of how all of that works. Engine operation, starting the engine. These are going to be things, Ellie, that you look at. We monitor the engine page. Even on takeoff, we go back between the engine page and the traffic page as we're looking at these things, because even though that we want to avoid hitting another airplane, it's always important to manage the engine, certainly. Starting a cold engine, that can be kind of rough. That's why we have heaters on our airplanes to keep that engine oil warm. We talk about some manufacturers suggesting a propeller pull-through. Make sure you're pulling it through the opposite direction so that it disconnects the ignition piece from happening so that it doesn't start your engine while you have your hands on it. Starting a hot engine, that can also be kind of tough, the old hot start. It's pretty tricky. The instant that fuel is reintroduced inside a hot engine, it can tend to vaporize in advance of what you want it to. And so it can sometimes make starting that engine kind of hard. So there's no priming of a hot engine, and it's basically, you know, you just, as you start turning the propeller is when you start adding the fuel to it, and you hope the thing catches. You know, you hope you get a spark enough to get that thing going, and that can be a little tricky. Stopping the engine, we always do a ground check in there where we do the ignition over to stop to hear the and then back on again. We went through that. But then the other thing is that we do to actually turn the engine off is that we have the engine idle set at about 1,000 or 1,200 RPM, whatever the manufacturer says, and then we kind of, not slowly, but gently pull the mixture all the way out to stop, and that so that we use all of the fuel in there, so there's not just stuff sitting in the cylinders of those engines, which could have a potential to rust. Changing the power settings in a constant speed propeller, you know how to do that. One thing too that you want to do is when you think in terms of, and I'm using this illustration here because in the illustration to the left, you can see the throttle on the left, prop is in the middle, and mixture is on the outside. So what you want to do is that to increase power, you start from the outside and you work your way in. You want to make sure that you adjust your mixture, then your prop, then your throttle before you increase power. To reduce power, you start with your throttle, then your prop, then your mixture. So as you add power, you do it in that direction. The primary reason that you work that flow that way is because, like for instance, in a turbocharged aircraft like this, if all of a sudden you have kind of a reduced mixture setting, and all of a sudden you put the spurs to it here with the power, what can happen is your engine can quit. Your engine can stop. In fact, even on takeoff on my airplane, I have to kind of work my mixture and my power together, slowly advance the two. At altitude, because we're operating lean at altitude, but then we're ultimately going to go to full rich because it's turbocharged and full power. Well, if I just shove full rich in first, the problem is going to be is that it's going to flood the engine, my engine's going to quit. So I have to gently kind of, you know, play with the two, gently kind of move them up together, you know, but slowly. And you have to kind of think about that as you're managing these with the more complex aircraft that you start flying. Are we done?
2 minutes.
How far do we have to go? Engine handling. I was thinking that we were going to get through the engine. The rough running engine, you know that, you've looked at that. The propeller, out of balance propeller vibration, that can be a problem. Taxiing, we know that. Engine fire, yeah, that can be entertaining. It's my daughter calling. Okay, Ellie, we're going to pick this up, chapter 9, tomorrow. Okay, so chapter 9, we'll pick that up tomorrow. We'll start with the fuel system, and I think that gets into the electrical system. Okay. There we are, searching for this thing so I can shut this sucker down. There's that. And, yeah, all right.